everyone. My name is Amaya Hamilton. I'm the Water Remediation Specialist with the West Virginia Water Research Institute, and I'm here to start the presentation for the 3RQ updates related to the Monongahela River Basin, and then I'll pass it off to Sarah Nelson. So one of our big events from this year has been our second annual Mon River Sweep. This year we pulled over 6,600 pounds of trash from the Mon River, and we had over 70 volunteers participate. And these volunteers were pulled from the WVU community, partner organizations, and the Morgantown community. And as far as we are planning for the third annual River Sweep, I think we have a confirmed date for April 18th. So if you're interested in participating that for this year, we should have a sign up link soon in the coming weeks. Our Common Waters program, for those who don't know, it coordinates projects between WVU students and local environmental nonprofits. It provides organizations with research and technical assistance, and students with the opportunity to apply what they're learning in classes, skills, research, and knowledge to real world projects. So this year, in 2025, last year in 2025, we created 14 projects between WVU students and 6 watershed groups. All in all, 16 students participated, and those were across 7 departments. And research projects included both research and outreach-based projects. There's a link at the bottom if you're interested in viewing those on our website. We also held 2 symposiums for students to present their projects, one in the spring and one in the fall. And we also led 2 labs with WVU's Freshwater Ecology Lab, gave students some hands-on experience with collecting field data and the sampling collection process. Additionally, we began bacteria monitoring this year. We purchased some IDEX equipment to assess total coliforms and E. coli levels. So we decided on 8 sites popular for water recreation in and around the greater Morgantown area. We monitor those sites monthly, with 2 sites being monitored twice a month since those are more swimming sites. And we determine if these sites pass or fail following EPA standards for E. coli. And then we post those results online. We post them to our social medias, our websites, and swimguide.com. And for routine monitoring, we monitor 18 sites on the Mon main stem and tributaries from Pittsburgh to Fairmont. Once a month, we assess general water quality parameters, and that information is all available online. We also monitor 8 sites for coliforms during the winter months, as we just discussed with bacteria monitoring that's new this year. We intend to continue that this summer as well. And we utilize the data in several projects to assess trends, which Sarah Nelson will cover next.
Hello, everyone. My name is Sarah Nelson. I'm a graduate student here at WRI, studying civil and environmental engineering. But I've been here for more than 2.5 years. Really glad they like me enough to keep me on as a grad student. I'm happy to be here. But first, I want to talk to you about this new 3RQ publication, which I was very fortunate to be part of. Satraka actually is here. I think I saw her in the audience. She is the first author of this paper. She's a PhD student here. This paper is called Long-Term Water Quality Trends in the Monongahela River Basin, and it was published in the Journal of Contemporary Water Research and Education. This paper investigates statistical trends of acid mine drainage signal parameters over the course of the entire program. Overall, it was found that there are widespread decreasing trends in TDS, sulfate, chloride, and sodium in all 6 Mon River main stem sites. Additionally, this study identified 3RQ as a critical program for continued water quality improvements in the Mon River Basin. Moving on to Robinson Run and its key impacts. So, one interest of ours was looking at Robinson Run data collected through the 3RQ program, specifically looking at the impacts of the Maiden Mine blowout. This occurred on April 1st of 2019. That image is actually Google Street View. You can go on there, look at it yourself. Um, there are other dates that we're interested as well in looking at, and these are relating to changes in active mining and treatment, newly inactive sites, and injection well activity. This has been sort of a tedious process. As you can see, that's a screenshot of one of my Excel spreadsheets just showing a bunch of permitting information and trying to find key dates based off of those. And then these are our 3RQ graphs showing actually why we're interested in this. Um, we're seeing increases in metals such as dissolved aluminum, dissolved iron, and dissolved manganese, and also increases in salt components such as chloride and bromide. Additionally, decreases in dissolved sodium, calcium, and sulfate are observed, as well as pH. Moving on to the lock and dam removal in Elizabeth, PA. As you know, this lock and dam removal began in April 2024 and is ongoing. And we're really interested in looking at the impact from that on the water quality of the Mon River. Currently, we could not connect the lock and dam removal to any significant impacts on water quality, but this project is ongoing and um, I believe the lock has been removed now, but the dam removal is still ongoing. Correct me if I'm wrong, but we'll see as the project progresses, what sort of results we get. So this is M23, where we sample for Elizabeth, PA, and you can see everything is in our historical range for TDS. And then this is a compilation of all of our Mon main stem sites. And you'll see everything's in historical range. Nothing that we could exactly pinpoint on the removal. And then this is probably the most robust study that I looked at over the past year, and it was the impact of the Richard Mine treatment on Deckers Creek. So through this, I compared Friends of Deckers Creek monitoring data collected upstream and downstream of the Richard Mine treatment to 3RQ data. Looking at Friends of Deckers Creek data, we saw general AMD signal parameter improvements. Um, this excludes TDS, which is increasing. This makes sense because AMD treatment introduced a lot of salts into the water, as well as you're having metals falling out of solution. Additionally, I wanted to point out that aluminum and iron are decreasing dramatically, and specifically, these are the total values, not the dissolved values. In general, this itself supports that AMD treatment throughout the watershed and at Richard Mine is improving water quality. Comparing this to 3RQ data now, so we collect our Deckers Creek sample at the headwaters, so downstream of the Richard Mine discharge. Referencing the study that I talked about at the very beginning, that study showed a significant upward trend in aluminum, but no significant trend for iron. And there are a couple of reasons that this could be the case. First of which is that 3RQ only reports only reports dissolved metals, not total metals. You'll see that Friends of Deckers Creek reports both. Additionally, this earlier statistical analysis was over a broader time period, and the Friends of Deckers Creek data points were collected beginning in 2022, so it's a less amount of time. Uh, Piggybacking off of that, I think if more data points could be collected from the sampling project, it would be very impactful to run a statistical analysis on this data to see if there are significant trends there. Thank you all for listening. I would ask for questions, but I think we're holding those until the end. Um, but that is all for the 3RQ updates.
All right. That was a great preview into some of the stuff I'm going to be talking about today. So I'm Beth Dakin with Duquesne University, and we have been a part of Three Rivers Quest since about 2013 when it expanded from being a Mon-only based study into covering a much wider geographic region. So as it is has been since 2013. We have broken down this wide geographic area, over 25,000 square miles across 5 states. And Duquesne has been charged with sampling in this brown southern Allegheny region. And because this is such a huge thing, I'm going to talk today about the Kiski drainage, which is these two southernmost kind of Huck regions under that heading, Southern Allegheny. As we all know, there's a wide range of water quality issues in Western Pennsylvania and the Ohio drainage. We have historical sources of pollution going back, centuries, even industrial effluents from factories and steel mills, things like that. We have things like road salt, sewage, and of course, abandoned mine drainage. And a lot of these sources were very detrimental to our rivers and streams and killed off a lot of fish and plant life, as well as affected residents' ability to use these streams. Now, we have seen a lot of improvement in a lot of these due to legislation, including things like SMCRA and the Clean Water Act. But we also have some newer sources of pollution and degradation in our rivers. And the big one that's been getting a lot of publicity and kind of kickstarted us to get involved with this Three Rivers Quest project has been the unconventional natural gas extraction, particularly the Marcellus Shale formation. And this has grown rapidly in Western Pennsylvania. And it really kicked off around 2008 or so. And, from the first couple of years where there were several hundred wells being drilled, we had now in Pennsylvania have over 20,000 permitted unconventional wells. And in addition to impacts from the drilling itself, it is a water intensive process, and there are a lot of concerns with how the water is disposed of and treated. This wastewater, in addition to containing high levels of chemical additives, can also have other nasty things like radioactive materials and brines that are parts of the natural geological formations that are being exploited. And while deep well injection is the primary way that wastewater is disposed of today, when this fracking first started in Western Pennsylvania, it was going to wastewater treatment plants. But by 2011, the PIDEP recognized that this was not really treating the water, and it was leading to a lot of discharges into our streams that was potentially degrading them. And so in 2011, PIDEP asked POTWs to voluntarily not treat fracking wastewater anymore. And by 2016, the US EPA had actually banned this practice. So now most producers either treat and reuse their water, and when it is too dirty, they eventually dispose of it in injection wells, either in Pennsylvania or out of state. So specifically in the Kiski watershed that I'm going to talk about today and show you some data, there's a long history of abandoned mine discharge problems, which we think has been getting better since the 1960s. And historically, that sulfate in particular was a big problem in the Kiski system. Road salts and brines, which are kind of a universal problem. Anywhere there's roads, there's going to be road salt. And then there has been a lot of conventional and unconventional gas extraction in that area, and brine treatment facilities that go with it. So here's a map of the sites I'm going to be talking about today. Just to orient you, here is the Allegheny River is coming downstream. The site that's labeled A30 on the map is at Lock and Dam 5, so it is just upstream of where the Kiski confluences with the Allegheny River. Then A22, that is the Allegheny at Tarentum, and A6 is kind of near downtown Pittsburgh. So those are some downstream on the Allegheny sites. And then we have sites on the main stem of the Kiski near where the mouth with the Allegheny, Conemaugh at Tunnelton, Blacklick Creek, Conemaugh at Seward, and then Loyal Hannah Creek. And as far as I'm talking about our monthly monitoring data today. So we go out in the field, we have a YSI meter that measures things like pH and dissolved oxygen and water temperature. And then we have our lab analysis with dissolved metals and anions and TDS, those kind of things. And so I'm going to talk a little bit about some of our parameter concentrations as well as some ratios. And I'm going to show you both our 3RQ data, which is from 2013 to 2025, as well as some historic data from the same sites that we have retrieved from EPA Storage, and that's data that goes back to 1950 to 1998. And the reason there are so many different parameters that I'm kind of trying to cram into one little talk is because some of those parameters have differing levels in these differing sources of pollution that we're interested in. So jumping right in, pH. So here this is the only one that's really regulated under the state. So all of the sites that we sample are either designated uses for warm water fisheries or trout stock fisheries. And for either of those uses, to be in attainment, the sites would have to have a pH between 6 and 9. And for the most part, you can see that they do meet those uses. Blacklick Creek, which is the third one over, does have, I think, 13 data points that are outliers, or 13 points that are below pH 6 over the 13 years of data. So most of the time it is above that. Additionally, we have a few other sites that have occasional outliers either above 9 or below 6. You can see also Black Lake kind of has the lowest average, not average because it's pH, median pH. And I'm going to move on because I have a lot to show you. This is every pH data point we have. And you can see that, again, what I wanted to take from this is that black line there is our site at Blacklick Creek. And so you can see it dips down pretty low several times. However, since 2020, it really hasn't gone very low very often. And this, I'm just going to kind of file that away for some of our other graphs I'm going to show. This is moving on to total dissolved solids, where again, you can see Blacklick Creek and the Kiskiminetas in general has higher levels of TDS than does the Allegheny River. You can also see like the upstream Allegheny River is slightly less TDS than downstream, indicating that the Kiskiminetas as a whole is a source of TDS into the Allegheny River. But again, you can see these black spikes over towards the left on the bottom graph. Those kind of stop after 2020, which indicates maybe we're having less TDS overall since 2020. This is data from dissolved aluminum. And because there's so many outliers, I'm going to zoom in just so you can see what's going on with the boxes in this box and whisker plot. So again, the message is kind of consistent here that Black Lake seems to have higher concentrations of a lot of these pollutants. But again, these aluminum points, we don't have any really high values of aluminum following 2020. And then also considered, so this top graph here is our 3RQ data. All of that data on that top graph is condensed into those last dozen or so points on the bottom graph. It's just average for years. So even though we're seeing what looks like really big spikes in aluminum on that top graph, they're really just kind of blips as far as historic concentrations of aluminum, what they have been in the past. Sulfate shows a very similar pattern, and I'm going to breeze through this in the interest of time. Sulfate, again, has come down from what it was historically, although it's still relatively high in Blacklick Creek. Chloride, also similar pattern. Ooh, we're gonna do that. But again, chloride has come down a lot since 2020. But the interesting thing here is chloride overall is actually higher than it was historically throughout the Kiski. And we suspect that maybe that has to do with increasing use of road salt. Bromide also shows that same pattern where it was high, especially in Blacklick Creek, and has decreased since 2020 or 2021. And then we can look at ratios. Because we don't have flow data for any of the historic data, we can't really talk about loads of any of these. So instead, what we can do, because we're taking samples at differing flow rates, look at ratios. And the one that is most interesting to me is this calcium to strontium ratio. When you have high strontium, your ratio of calcium to strontium is expected to be lower. And what we see here is that when we started sampling in 2013, well, we didn't sample strontium for the first year. That's why there's a gap. But in 2014 through 2020, we had a much lower ratio of strontium or calcium to strontium in Blacklet Creek in particular. And then it's come up to be kind of still a little bit lower, but similar to the other sites. And the main source of strontium in, if you remember back to that box with X's, is from unconventional natural gas. And another way to plot this is like this. Calcium magnesium versus calcium strontium. And what we are suspicious of, so this blue here, oval, is what surface water in general in pristine sources should look like. And these black dots are kind of shifted down and to the right towards this yellow conventional gas and this black unconventional gas extraction. So our suspicion is that when we started this study and there was a treatment center that was on Blacklet Creek, it was showing signs of being impacted by that water treatment plant. And once that shut down following the ban on accepting wastewater, after a while, by 2020 or 2021, it seems like it is starting to return to kind of a more normal signature. And so between that and the increase in chloride are the two big trends that we're seeing, which we, again, think may be related to increasing amounts of road salt over time.
So I want to talk a little bit about a water quality monitoring program that I had been working on when I was at West Liberty. This semester, I've changed positions. I'm now down at Tennessee Tech. So we have similar but different issues down here, but I've actually still had students up in West Liberty collecting data. Actually, they're going to be collecting it through April of this year. And so we've got the right screen, so I could, there you go. We've been actually monitoring 23 sites in the greater Wheeling area on some basic water quality parameters, actually starting back in 2018. What I'm going to present to you today is starting at 2020, but we've done the basic specific conductance, temperature, pH, chloride, and turbidity. And on some sites, we were measuring E. coli. And what I wanted to focus on today was some trends in specific conductance. And so this is one of the students who helped me start this program, Emma McClellan, and she has since graduated, and I'm not sure exactly what she's up to right now, but just an amazing picture of her. And so what I wanted to talk about today was kind of comparing some of our more impacted sites with a reference site here. And so this is one of our better sites. This is Castleman's Run in the image. It's part of the Buffalo Creek Watershed. And so I've got a site on Buffalo Creek that we've been monitoring for several years, Castleman's Run, two sites on Wheeling Creek, which is a fifth order creek that runs straight through the city of Wheeling. And then one of its tributaries is Little Wheeling Creek. This was also the one that had the severe flood earlier this year. Peters Run, a small tributary. Short Creek is heavily impacted in its lower reaches by the part of the Tunnel Ridge mine, and you'll see some data where they had some major issues at one point. And then North Fork is a small tributary to that runs right by campus. And then Glenn's Run is an AMD site close to campus we've been monitoring. There's a picture of it. It is in a terrible condition. And then we've got two sites on the Ohio River around Wheeling as kind of reference points. We wanted to get a spread of creek sizes also. So this is a picture of Wheeling Creek. This is a popular boating location. And so one of our issues is or one of our focuses, we want to work on trying to make sure this creek stays as nice as possible. It's also stocked with trout. So there's a lot of recreational potential associated with this creek, similar to the Buffalo Creek also, which is just a little bit smaller. And then the Ohio River, everyone knows it's used for recreation. I wouldn't eat the fish out of it. But interestingly, in the last couple years, as we've had these fairly dry summers, the water quality in the Ohio has improved dramatically. And that while that can be good on some sides, their macrophyte beds have come back. I think fishing opportunities have increased, but there might be some issues with what that might mean in terms of discharges into the creek. And so here's a couple of our sites. Here's Wheeling down here. Let me see if I can change this to the laser pointer. So we've got Wheeling, and then Wheeling Creek runs up this way. So this is one of our more downstream sections right in town. This is Wheeling Creek 3, WECRO3. It's got major E. coli issues and a large resident goose population. Those are probably connected. The next site here is going to be this '09 site, which is just upstream of the downtown area and is pretty popular with recreation. These are big beds of Justicia americana, lots of rafting and tubing through here also for recreation in the summer. We've got Little Wheeling Creek. This is the one that flooded severely. It has a road that runs next to the entire length of it, lots of houses right along the banks. And then in our sampling location, there's a big parking lot with a grocery store, Tractor Supply, and it just sheds lots of water from that parking lot straight into the creek. And then I don't have any good pictures of the Ohio River site, but we've got one right here on the upstream side of Wheeling, and then this is the Warwood area where another sampling location is. Short Creek Watershed is a small basin that has some mining activity in it right over here. The Clearview Tunnel Ridge Mine, West Liberty's campus is up here on North Fork. North Fork is in pretty good condition. It's a little bit of housing, lots of forest, gravel road next to it. And the upstream parts of Short Creek are in relatively good condition. And then as we move downstream, we increase lots of litter. There's a substantial increase in housing. And then this is downstream of the effluent from that large mine operation that is right over here. And then this is our AMD impacted site, Glens Run. I'll call it Cherry Hill Road because that's what I thought it was called originally, and or Cherry Hill Creek. AMD biologically toast. There's only unfortunate organisms that perish in that. Occasionally, a few very distressed salamanders have been found, but no aquatic insects to speak of. And what I wanted to point out here is this creek runs right along the side of the road, past some houses, and then dumps in. There's actually a greenway through here. This is the effluent plume that's coming out into the Ohio River. I'm actually just upstream of Wheeling's water intake. And then Buffalo Creek, which is just north of Wheeling. West Liberty is sitting right down here. And so this is Castleman's Run, which is probably our best reference site in the area, primarily a forested watershed. And then Buffalo Creek itself has pretty good water quality also and is relatively popular with boaters when there's enough water in it. And so what I want to do is try to take these multi-years of data and assess them a couple ways and try to understand, what is our trend in water quality and how are these creeks looking overall? One of the things that we've noticed is that some sites are pretty variable in their specific conductance. And so we calculated a coefficient of variation because we wanted to get some ideas of how are these sites changing over time. And what the coefficient of variation does is help kind of rectify and give a relative amount of variation across streams that might have different average conditions. And then we conducted a generalized additive model to try to understand what were the general trends going on with these creeks. And so if we look at our median specific inductance, our reference sites over here is Castleman Run, and this dotted line is 500 microsiemens per centimeter. And what you see is Buffalo Creek and Castleman's Run are pretty good. Short Creek, the upstream side, is a little bit elevated. It's got more urbanization and development on it. The site below the mine has definitely much higher levels of conductivity compared to even sites just upstream. This North Fork site's a tributary to it. Our AMD impacted site has very high specific conductance, many times over what a reference condition would be. The Ohio River sites overall are actually some of our lowest conductivity sites, which this continuously surprises me. Average conductivity is often 400 or below. And then our Wheeling Creek sites here, a little bit elevated over reference condition. And then this little trib to it, to Wheeling Creek Basin. The road runs right next to it. It's got some urbanization, some AMD impacts. It's elevated also. What was interesting is if we look at this coefficient of variation, if we use our Castleman's Run site as a reference point, we can see that most of our other streams have higher variation in specific conductance than the reference. Buffalo Creek just slightly elevated. Our AMD impacted and mining impacted sites have huge variation in the conductivity that we're seeing throughout time. And one of the things I thought was interesting is that The Ohio River seems to have quite a bit of variation going on in specific conductance also. And while its median conductance was much lower than our Wheeling Creek sites, once we look at this coefficient of variation, we really see that there's something going on with the variability in pH of the Ohio River. And then Wheeling Creek's substantially higher. There's no statistics on this, but substantially higher than our reference sites. When we look at what that specific conductance does over time, this solid line here, and I'm sorry this might be hard to see, but this is the predicted trend in conductivity over time. So here's conductivity in microsiemens per centimeter. And what you can see is that while the individual readings bounce around a little bit, this smooth trend line says that from kind of 2021 into about 2023, our reference site was sitting somewhere around 450, but then crept up to probably a little over 500 over the last 2 years. And what you'll see is that this increase in conductivity, particularly over the summer months of and fall of 2024 and into the summer of 2025, is a repeated trend. So Castleman's Run has increased maybe around 50 microsiemens on average. Buffalo Creek is kind of a similar story, sitting somewhere here just below 500 for several years, and then more recently hopping up here to around 550. Our Short Creek 5 site, that's the more upstream one, conductivity starts out higher, but we've got a clear trend of increasing conductivity, and it's increased probably 50 to 75, particularly in these last 2 years. Our Short Creek 2, the one that's impacted by the mines, this is when Tunnel Ridge really started to get going, and we had notable spikes in conductivity, increasing many-fold over what the low levels were. And then through 22 and 23, it kind of calmed down a little bit. We're sitting at, maybe around 800 here, but then there seems to be a little bit of an increase over time. Also with Short Creek 2, which, like I said, is severely impacted and influenced by the mine effluent. Our AMD impacted site, not only is the baseline is very high, but we see real clear trends of increasing conductivity over time, really starting in late 2023. And then this hot summer of 2024 was very dry. And again, this last summer where we've got conductivity that's pretty much doubled what it was in 2021. And then Ohio River, what is kind of startling to me is that this 2024 summer and 2025 summer, we see a real clear increase in conductivity. There's not a huge trend difference between our upstream and downstream Ohio River sites. They're both showing this increase in conductivity in 2024 and 2025. And Wheeling Creek shows a similar pattern of increasing conductivity over time. This is the most upstream site here. And then, I'm sorry, that was Little Wheeling Creek. This is the main stem, similar pattern. And then our most downstream site, again, a very similar pattern. And so really what we're seeing is that many of our sites have fairly high conductivities to begin with. Some of them have more variation than other ones, but our better sites are showing less variation in conductivity. The more impacted sites seem to have more variation. And what's particularly concerning is that we seem to have this increase over the last 2 years where we've had these hot, dry summers and conductivity is increasing. While we don't know the causes, it might be increased reliance on salty groundwater related back to road salting, impacts of fracking, water withdrawals. We're not real sure, but we kind of see this consistent pattern. There's lots of folks who have helped collect this data and for several years, and I appreciate all these students' hard work, and I'm happy to take questions when the time is appropriate.
Today, I'm going to talk about the work that we've been doing using temperature and light sensors to evaluate patterns of restoration success. And basically, the premise of the talk today is really in the context of stream bank erosion. Poor land use management often results in large amounts of surface flows that increase the amount of water that winds up within a stream. Those higher flows typically result in processes like incising and cutting away of the bank, which can eventually lead to bank failure. leading to processes like widening of the stream, and eventually leading to the formation of a new stable graded bank in and of itself. There are many consequences of this erosion, and the most obvious of which is what happens to all of the earth when it falls into the stream. It must be transported and deposited somewhere. So that's kind of like the major problem that we've been trying to address with the restorations I'm going to talk about today. Over the past 4 years, we've addressed 3 different restorations within the lower reaches of the Woodcock Creek watershed, indicated here by this red kind of circle. You'll see that there's numerous black spots, dots throughout the watershed, indicating previous fish surveys that had been done within the watershed. Basically, this is just highlighting that we have a bunch of baseline data within Woodcock Creek watershed. It's really close to Allegheny College, so many students have done projects within it over the years. It's a third order stream that drains into French Creek. It's located kind of at the heart of Crawford County, Northwest Pennsylvania here. Like I said, our 2 main study reaches are below the reservoir that's located at the heart of the watershed. This is what the watershed's kind of known for. The Army Corps of Engineers installed a reservoir for flood control protection in the 60s, and that's what it's operated for. In addition to all of our treatment reaches in the lower watershed, we also have numerous control sites, basically in the upper part of the watershed, that serve as references in addition to the treatments, if you will, that serve as our restorations. So basically, we have these lower treatment reaches, and then everything is a control above the reservoir. When we zoom in to look specifically at these restorations over the past couple of years, you can see that 2 of them have occurred directly on the main stem of Woodcock Creek. One is directly below the reservoir at a public park, and then the other one was on private property. And then the second restoration occurred on this unnamed tributary to Woodcock Creek, which we call German Run. And I'll show you kind of why the logic was for these restorations in a moment. But basically, we had 3 hypotheses that we wanted to test for our restorations here. We predicted that our restoration sites would be warmer than all of the control sites because of the poor habitat quality here. That's why we were undergoing restoration activities for them. We predicted that the restoration sites will have higher levels of total suspended solids. So basically, that's just the amount of fine sediments being carried in the water column. And then we predicted that restoration sites will have lower light levels due to higher total suspended sediments. So basically, we were thinking about how light could be used as a proxy for measuring the turbidity levels of water, for example. Here's some pictures to kind of orient you to our restoration sites. This is the one on Woodcock Creek. The example image here shows what it was like before the restoration, and then the one on the right shows what it was like after the restoration. Basically, there were 2 main problems at this site. The landowner was losing their land on this side. The water kept coming in and eating away at the bank, so we put mud sill cribbing in to reinforce it. And then you'll note the formation of this large gravel bar in the middle of the stream. So we tried to install log vane deflectors to try and push more of the flow to the center of the channel. Where does this large gravel bar come from? Well, we hypothesize that it comes from the current unnamed tributary that we did the restoration on. As you can see, this unnamed tributary has just a massive wall of earth that is exposed. This tributary drains an urban area, so when the flows come up, the flows come up. So what we attempted to do with restoration at this site was to install log deflectors to just keep those angry flows from further eating away at the bank. Our methods were relatively simple. At each of these control and restoration sites, we had grab samples for water collections where we just measured turbidity and total suspended sediments with vacuum filtration. We tried to get out there on a weekly or bi-weekly basis, but we were, of course, somewhat selective. We wanted to get conditions of really high flow water when it was like chocolate milk conditions. And then during the same period, we were getting grab samples. We had a hobo pendant logger deployed at these sites that collected 15-minute measurements on light and temp. And essentially what we wanted to do was look for a correlation between turbidity and light. Do the on-site grab samples of turbidity and TSS that we collect match the in situ light readings from the temperature loggers? So I'll look at some temperature patterns first by location type. Here are August temperature patterns for those three stream types that we've been looking at: French Creek, Woodcock Creek, and then unnamed tributaries to Woodcock Creek. And what we see is a pattern that matches the stream longitudinal gradient. Many of our tributaries are cold with temperatures less than 20 degrees, whereas French Creek has temperatures above 23 degrees. Here, looking at August temperature now for all of the different locations on the x-axis, we see that our restoration sites don't necessarily have cooler temperatures than other control reaches within the basins, but there is most definitely elevated temperatures at that German Run restoration site relative to the control tributaries within the basin. Next, here we have mean winter spring temperatures on the y-axis for those same stream locations and deployment locations. Winter spring in this context is basically referring to the aggregated December to March period. Okay. While we see a similar pattern here with elevated temperatures at the R2 restoration tributary relative to our control tribs, the real take home here was that there are much elevated temperatures at our restoration sites located below the reservoir. And so we suspect that the reservoir might actually provide like these warm pulses to Woodcock Creek relative to French Creek and other tributaries in the basin. Okay, next we have mean winter spring total suspended sediments on the y-axis as a function of our stream locations and deployments. Here, we'll see relatively constant measures of TSS on the main stem of French Creek, and no real differences in TSS for our Woodcock Creek locations, and then our control sites on Woodcock Creek as well. But we see the clear effect from TSS with our restoration site on the unnamed tributary. That basically we see it putting in 120 milligrams per liter of sediment compared to less than 50 for the other two unnamed tributaries. And this matches expectations of the literature. A study that our methods are based on, Ostrovsky et al., found that many agricultural streams in our area have average TSS of 70 milligrams per liter. So this urban stream is putting out even more sediment loads than what we would expect for agricultural impairment. Here we have mean winter spring light on the y-axis for those same stream and deployment locations. Basically, we expect this graph to show the same pattern as the previous one, and unfortunately, it doesn't. So light did not necessarily show the results we were hoping for with respect to our hypotheses. There were a lot of problems with trying to model light. At two locations where we kept deploying it, it was too shaded, so it was never detecting any light signals. And then at some locations, they would get iced over, and so light wasn't being recorded. So instead, what we decided to do was look at a site-by-site comparison to see if there was correlations in light and TSS just at these two locations where light was at least reading properly. And so for the top graph here, we have light intensity as a function of TSS for our restoration site at that unnamed tributary. And here we see the kind of perfect relationship we were looking for, that as TSS increases, we see that reduction in the light reading on the meter. But then at Stainbrook, at our third restoration site, we saw that there was no trend at that location at all. But you'll note the lower TSS values in general for this site. So plans moving forward, the loggers are out there. We're continuing to collect TSS every week. We have next steps for restoration. That unnamed tributary is still carrying far too much sediment than the conservation district would like. We're currently trying to implement what we call a chop and drop method on that tributary. Basically, we want to work with land managers to fell trees and use those trees as a means to capture the sediment and debris behind it. Furthermore, at those two French Creek deployment locations of monitors, coincidentally, PennDOT has also been replacing bridges in that area of French Creek. And so there's been a lot of concerns about hellbender population impacts in those regions, because obviously with the bridges coming down, with a lot more sediment getting put into the stream, the effects are concerning for hellbenders there. So we're hoping to kind of expand this potential modeling output to that project as well. And that's it.